Hi everyone, my name is Alexey Gorlach. I'm the student of Ido Kamener, and this work is done in the collaboration with Orange Coins Group. So basically, the main purpose of our work is to find the possible ways how to create in...
Speak louder.
Okay, so the main goal of our work is to find the possible ways to create intense quantum light. And let me start with a brief motivation. So basically the main topic of my talk is strong field quantum optics. Strong field quantum optics opens two different research avenues. The first one is connected with the fact that if we have intense driving field interacting with nonlinear material, we will have intense emission, resulting emission. It means that we can hope for intense creation and manipulation of intense quantum light, which can find its applications in quantum computing or in quantum communications. The other avenue is connected with extreme nonlinearity of the processes. That means that the resulting emission can have X-ray component. So we can go towards X-ray quantum optics. It's especially interesting because usually the conventional methods and optical tools such as lenses and mirrors barely work in X-ray region. So a little bit more about photon quantum computing. One of the main bottlenecks in the quantum computers is that they operate with just a few photons. It implies that we need single photon detectors to detect such states. If we would be able to create and to manipulate by strong, intense quantum light, then this problem could be solved. But basically the main goal is to create intense quantum light. But what means quantum? The answer to this question gives quantum optics. Basically on this slide you can see comparison of the coherent state, which is produced by laser, and such state is considered to be the most classical, and other quantum states. The full description of photonic quantum state is a Wigner function. For the coherent state, it's just a Gaussian, but for other quantum state, it can be much more complex function. Also, there are such properties as, for example, entanglement or squeezing. Squeezing means that the uncertainty in amplitude or in the phase of the wave is smaller than of the coherent light, and entanglement basically means the correlation between different photons inside the light. So, and how we can create such states? Usually, conventionally, it's created by using perturbative nonlinear effects, such as second harmonic generation or, for example, spontaneous parametric down conversion. But we explore another regime. The question about what happens if the field is very strong and our process already non-perturbative remains unexplored. The quantum properties of in such effect will be interesting to investigate, and it was our goal. So basically, let's consider a typical strong field experiment. Strong laser goes through the gas of atoms, and atoms produce high harmonics of the driving field. So the spectrum, the typical spectrum in such experiment you can see in the left part of this slide. But what about the quantum properties of emission of such process? So we derived a quantum theory which predicts the quantum properties of emitted light during such process. It turns out that this light is slightly super Poissonian and has a little bit of squeezing. Not going in the details, I want to say that even in such simple case, we have a few quantum properties. But if we want to manipulate by them and want to have some another quantum properties, we need to consider more general scheme. So basically, we propose 3 different variants. The first variant is the standard situation that I discussed last slide. Also, the possibility is to modify the atomic system with inducing correlations inside it. Or the other possibility is to create a quantum driving field. Let's discuss it step by step. Let's start with the quantum correlations in the atomic system. We propose the following scheme. Let's imagine the atomic system and the weak preparation pulse excites this system. If we will wait for some time, then the correlations between different atoms will be built due to the interatomic interactions or, for example, superradiance. If we will wait for longer time, these correlations will disappear and the atomic system will return to its ground state. But we will not wait for that, and exactly at the time when these correlations build, we shine on it with a strong laser and short pulse. Resulting emission will have interesting properties because correlations from the atomic system will be transferred to the emitted radiation. So basically, we build a theoretical model which should describe this effect. It's a pretty complex theory because we need to take into account, we need to solve many body problem, and each part of the system interacts with other parts and moreover with light. So here basically you can see the palm probe experiment that I was talked about last slide. And you can see the typical spectrum which I showed you before. So the main results of our theory is this plot. So basically, to characterize the light completely, it's a very hard problem. So just as an example, here I show just the 33rd harmonic as an example of the emission and show its Wigner function as a function of delay between the preparation pulse and the main pulse. So if this time is 0, then on this plot, on the most left part, we can see something similar to ellipse. It means that our state is very similar to the coherent. But if we will wait for long enough time between preparation and main pulse, then the correlations are built and we start to have Wigner function which is significantly different from the coherent state. Moreover, we check the correlations between different frequencies, between different harmonics. Here you can see the example of the correlations between 33rd and 39th harmonics. So if the time delay is 0, then there is no any correlations. If the time delay is large enough, then we start to have some correlations as shown in the most left part of this figure. Another possibility is to make quantum drive. In this case, we can expect that the resulting emission will have firstly the X-ray component and second will have more quantum behavior. So this idea we want to check theoretically as well experimentally. So nowadays we are building in our lab with collaboration with Orange Coin such source of quantum light. It's bright squeezed vacuum, which enables to see non-perturbative nonlinear effects if it will interact with gas of atoms. So basically I showed you a few examples of strong nonlinear interactions. It's just a small piece towards the full picture of understanding how to create and how to manipulate of quantum light with high intensities. Thank you for the attention.
One quick question before we continue, because time is getting short. So one quick question from the audience. Yes, over there.
Doesn't the high intensity heat up your system and cause decoherence?
Yes, we have decoherence in our system, of course, but if we interact with very short pulses, which can be femtosecond, then it's possible to overcome, let's say, this problem. Because it's ultra-fast phenomena.
Let's continue with the talk, and maybe you can ask him after that, okay?
Okay,
So
thank you very much.
Alexey.
Thank you.